not too many greater challenges than nuclear power in space. The physics involved in it is quite intense. It kind of has that luster of something totally different. But we start with that highly enriched core. The splitting of the atoms generates that heat that we need at the right power levels, at the right temperature levels, and then we transfer that heat up to the power conversion system. And then you convert that to electricity at that engine, reject some of the waste heat, and then use electricity for whatever you're trying to power, whether it's a coffee maker or a very expensive instrument for science. It sounds pretty simple because it kind of is simple. It's just the engineering pieces aren't always as simple.
Nuclear energy and spaceflight have a deep history that stretches all the way back to the Cold War. At the time, scientists were looking for new ways to harness the power of the atom, and nuclear offered something special for deep space missions.
Because we don't have to rely on the sun, right? When we go out deep space, or whether we're in a shadowed crater on the moon or whatever, we've got our own energy source. That's the biggest plus. The secondary piece of that is the amount of power that energy can provide, right? Fission power is very, very high on the power density scale.
As a quick refresher, nuclear fission releases heat energy by splitting atoms, and fusion combines two lighter atoms into a larger one. They both release an enormous amount of energy, but scientists found fission easier to control for space missions. To tap into nuclear's potential, NASA launched a research program called SNAP. This kickstarted the development of radioisotope thermoelectric generators, which use plutonium-238 and thermocouples to convert heat into electricity. These units have been on a number of famous missions, like Curiosity, Cassini, Pioneer, and even Voyager 1, which is currently cruising on RTG power 21 billion kilometers away from us. The program also developed SNAP-10A, a fission reactor that's considered the U.S.'s first and only known nuclear space reactor. It took off in 1965, failed after 43 days into the mission, and will be orbiting Earth for another 3,000 years. All subsequent nuclear space programs, like NERVA, which looked into nuclear-powered rockets, were shuttered or just didn't get off the ground.
Now, given they were working on bigger power systems, which was part of the problem, I think, but they were also chasing materials and processes and things that weren't available at the time.
Today, nuclear power systems are seeing a comeback, and that's thanks to new mission targets.
When we start talking about putting men on the moon in 2024 or on Mars in the 2030s, you need a lot more power, and that's where fission really kicks in. Kilopower is 1 to 10 kilowatts of electrical power. That's starting with the fuel source. It's uranium, molybdenum, alloyed fuel, highly enriched. We have sodium heat pipes that are attached to that core. That sodium heat pipes carries that heated vapor up to the Stirling power conversion system. Then we have to cool the engines to get that temperature difference that we need for that power conversion and keep the engines from overheating. The other pieces of the reactor that are obviously very important are the neutron reflector that helps direct those neutrons back into the core and keep that chain reaction going at the power levels that we need. Before we're operating this, we have a poison rod inside the center of that core, and then when we get to our destination, we have a mechanism that would pull that rod out, make sure that those neutrons are not being absorbed anymore and they can start the actual chain reaction that we need. One of the biggest attributes, I think, to the success of this program was we kept everything very small, and we're looking to make it as lightweight as possible.
Once the design was approved by NASA, the system and the people behind it were shipped off to Nevada for testing.
Krusty was the experiment, which stood for kilopower reactor using Stirling technology. That experiment was really a follow-on to the Duff experiment, a demonstration using flat-top fissions. And so Los Alamos typically always likes to name their nuclear experiments after Simpsons characters. We run through all those mission scenarios where we would turn off the cooling to the whole top end of the power conversion system and see how the reactor reacted and how we could really mess with them and see, is it going to be a stable controlled reactor.
The experiment culminated in a 28-hour test from reactor startup to shutdown. It operated at 800 degrees Celsius and produced over 4 kilowatts of power.
The highest power nuclear mission we've ever completed was Cassini that had, 870 watts. So already our lowest is higher than any mission that's ever been done. We did things to that reactor that you shouldn't do to a reactor, but it was really neat the way it handles. From concept to test was about 3.5 years, and that's a real quick timetable. To me, that's the most impressive piece. Me and one of my buddies down at Marshall, as we were kind of cleaning things up afterwards, the thousands of CAD models that we had and the information that was generated, we're like, how did we do all that work? I'm like, I don't know. Some days I don't know. We worked a lot of hours and just had a lot of passion, and the fact that it worked really well was just a bonus.
This was a major step in demonstrating nuclear power's feasibility in the new space age, but there are still hurdles ahead.
The real challenges are really political and how we develop all the safety and security pieces to launching a nuclear system. There's a whole lot of work related to making sure that there's no way you accidentally start that reactor up. And then there's what we call the launch safety piece, which also has a criticality accident associated with it. So if the launch vehicle fails and it falls into the ocean or on a beach or in general public, we have to show that it's not going to turn itself on.
Political will might be in favor for this time. Congress recently passed a bill earmarking $100 million for NASA to develop nuclear thermal rocket engines. So a future of fission for both propulsion and power is looking ever more promising.
We've just finished some studies with JPL on how we use this for what we call nuclear electric propulsion. So you couple our reactor now with an electric propulsion system, and we can go do deep space missions carrying much higher payloads, faster times. We've got design concepts that couple 4 of those to give us 40 kilowatts of electricity on one lander that now you can use for your human habitat. Once we prove the technology and it's available as a power source, you'll start to see some really neat proposals on what they can do with that extra power.